Alright, welcome back to Meteorology 101. This video, it looks like we got some severe weather over the southwest United States. Snowfall over Colorado. Looks like a pressure system over the southwest. So we're going to pull up the surface chart and upper air charts, break this system down, pull up some radar, see if we can get some cross sections in these storms. Right up in the panhandle of Texas, we got some reports of tornado touchdowns. They're pretty much already gone, but there's still some warnings out there. Still a possibility of severe weather all along that line, right over Texas. So let's break this thing down and see what we got going on. First thing, we gotta pull up a surface chart and see what we have for pressure systems. See what we're going. See what's causing all this. If you look at that radar, we did have some rotation right over northern New Mexico, southern Colorado. So this low pressure system, maybe this chart's just a little bit old, is moving to the northeast, and looks like I would say some warm air advection on the east side of that low, cold air advection on the back side of that low. Let's throw some temperature lines on and see what we have there. Maybe a warm front, cold front's drinking south that's pushing to the east. We got lift all along the central panhandle. So this is a bear clinic system. Looks like a warm core low. We have a warm core system right over the Colorado, Utah, Wyoming area, and pretty much got all the warm air advection we need. Let's pull up some station plots, see what kind of temperatures we have, dew points, winds. Sometimes these charts get a little bit crowded, so see what we can work with. So we do got the low pressure system, about 25 to 30 knot winds around that low, so significant, pretty good winds around that low. And it is bear clinic, so we are pushing all this warm air from the south, and our ceilings are marginal VFR where the blue dots are, the blue stations. Black, it's VFR, and the red is where you get up into that warm air advection. You get up ahead of that warm front. Right there's the trough, leading edge of that warm front, and then all that warm air advection. You start getting those very low ceilings. Steady rainfall. You get up in the upper elevations from steady snow. So we got snow all through Colorado being reported, light to moderate. It's like thunderstorm down in Texas. We have a whole line, that line we've seen on the radar, from the northern part of the Panhandle all the way down into the central west central part of Texas, and then like I said, with 25, 30 knot winds, we got some pretty significant rotation right there. So let's go ahead and erase this. Let's throw up just the station plots, look at so we can get a good look at these dew points. We're looking for dew points right around 60, depending on what the temperature is. So temperature 60, dew point 59. That brings us to 100%, almost 100% relative humidity. But once you start getting those dew points into the 60, you get that humidity you need to cause that instability. So there's three things you need for a thunderstorm: is moisture. We got that moisture from the south, instability. We have the low pressure system and the lift. So we have that frontal, little bit of a frontal boundary there that's pushing through, and that's causing the lift right along just central west central Texas. So that's why we're getting that line right there. But we have definitely have the rotation. Let me get a little bit more plots on here. Let me erase that, pull up a few more plots so we can get a little bit closer data. I don't want to get too cluttered. Sometimes it gets a little too cluttered, you can't even read the data. So get up a little bit more than that. Give me just a second. All right, so now we're getting into pretty strong area of rotation. You can actually see the winds out of the northwest and winds out of the southeast, and that's definitely low level convergence right there at that low pressure system. So right along that front, right where the thunderstorms are being created. So let's go pull up a satellite. Alright, so we can run this loop. You can see the strong convection line right through the central part of that panhandle, pushing up. Now, if you look at any rotation, you can see would be. I see a cell there, cell there, cell there. Rotation right there. I would look for any kind of tornado warnings right there in that south central part of that panhandle. Also, right up here where in the northern part of that panhandle, look for any rotation right there. You do have that nice little comma shape. So also look for any rotation down in the south part of this comma. If you get these cells, you want to break these cells down because you can get tornadoes all along those cells. You're looking mainly in the southwest quadrant. Let me stop this loop. Alright, so then the southwest quadrant of these thunderstorm cells, that's where you're going to get any tornadoes form. Alright, so that's pretty significant convection right there. It's going up pretty high, so we'll pull up some local radars and see what we got. Okay. Make sure you guys can see the right one here. Alright, so we do have a warning. This is a severe weather statement. Amarillo, Texas. Tornado warning remains in effect until 6:30 p.m. Central Time. So that's almost over. A confirmed tornado was located over Howardwick, or 6 miles north of Clarendon, moving north at 30 miles per hour, damaging tornado with golf ball size hail. So that was reported earlier. There's still warnings up here. Here's a couple warnings that were reported. Actual tornadoes. They just went back into a tornado warning that just popped up on the screen. So this is EAS emergency area activation requested. I know you guys can't see these little pop-up windows, but we are looking at the tornado to the north, the northern part of that. The northern tornado right now. So it's two severe thunderstorms capable of producing tornadoes, first located 6 miles southeast of Lake McClellan, and a second located over Clarendon. We're moving northeast at 35 miles per hour. Tornado golf ball size hail. Radar indicated rotation. So once they see the radar indicates rotation, then they throw out tornado warnings. They don't wait for someone to see tornadoes on the ground. If it's significant rotation on the radar, then they will throw out a warning. So let's look at the velocity here. We can pop up the different levels. Like I said, this is the velocity. We got all of our rotation. We don't have any real rotation right. We're showing right here. We got all of these. All of this red is wind blowing in toward the radar. So if you see any light colors like the green, that's where you're going to see any rotation. There's a couple little pixels here. Probably nothing significant on that end. The base reflectivity, we can pop up into the upper levels, change our angle of our radar, and we see how it thins out as it gets up into the upper levels. So it is still strong enough to produce a tornado, have that rotation. So let me get we can pull up through that warning. We can do a cross section of this radar. Let's do a cross section of this cell, and let's see what we got there. All right, let me go fix my screen here. Okay. Alright, so where we have that radar, that cell to the north, let's go do a cross section on that, see what we got. See if you guys see what I'm seeing. Alright. So really for severe weather, just severe weather, not necessarily tornadoes, but severe weather as far as a severe thunderstorm producing winds, hail, or tornadoes, you're looking at 50 dBz on at 10,000 feet. Once you get 50 dBz's at 10,000 feet, you can produce severe enough winds and hail to create a severe, be considered a severe thunderstorm. All right, my screen is messed up here. Let's see. All right, give me just a second. All right, we can swing this out. Chase that cell across. And we get a better section of that thing. We can swing it around that cell also. There's pretty much the deepest part of that cell right there. And you do have about 50 dBz's going up to about almost 18,000 feet. So that's a pretty significant thunderstorm cell. You definitely would see some rotation in there. Alright, let's pull up, let's go do that cross section. Let me get rid of that. Okay. Let's do a 3D shot of this cell, and we can pull up, just get a good look at this thing in the 3D sense. Alright, so, like I said, the southwest quadrant of that thunderstorm cell is going to give you the heaviest. That's where you're going to see the heaviest rain. What you get is the updraft, then you get a down. Start seeing a downdraft, then you can start watching for. Get rid of all that blue. It doesn't mean anything. This takes out the yellow and everything. I kind of don't like this, but if you look at the green, you can see your updraft. Anywhere, there might be a downdraft coming down on this side. If once you get the updraft, the downdraft, and then your downdraft, they start wrapping together. That's when you get that vortex. You can have that rotation, and you're a tornado on the ground. So we do have a pretty significant layer of moisture going all the way up to over 30,000 feet. I mean, it's reaching almost 40,000, pretty much 40,000 feet. So that's a significant updraft to push the moisture that high. Throw that green back on, or that blue back on there. We got you can see your overshooting tops now. It's one there, one there, one there. So maybe some isolated cells within this. Alright, let's go look at some velocity. That's not really showing us anything. It's just going to show us what's on the surface now. If you look at the velocity, we do have the red and the green, so that is definitely an indication of rotation all through that cell. I can pull up rotation and see if this gives us anything. There is an area of rotation where the blue is on the showing up on the surface right there. Most of it is to the southwest. It's a larger area. Let's see if there's any. Nothing really in the major upper levels of rotation. So definitely can definitely produce a tornado. Definitely with that hook echo there. Let me get rid of this thing here. You can see that right there, that hook echo. Look at that. Let's get a cross section there. Let's go a little bit bigger. Let's go. Let's drag this cross section all the way down through there. See if we can get a better breakdown of this cell. You can see right there's the strongest area, about 18,000 feet. We pulled that. We hit that on the last cross section. That's about the strongest part of that storm. 50 dBz's at 18,000 feet. So that's a pretty good, pretty heavy duty thunderstorm. Alright, let's go pull the charts. We'll break down these systems. Do a cross section here, see what we got. Get up into that white. There we go. There's a pretty heavy duty cell right there. That's 73 dBz's over 20,000 feet. That is a really severe cell right there. They just have a severe warning right now. Nothing on the ground. Nothing reported as anything reported as being severe. So there's the big picture. Let's pull up this one. Once you get too big of an area, this thing kind of spreads out too far. It's hard to see. But you can see your upper level moisture in those systems. Put that about level. You're about almost 40,000 feet there. So you can see those cells. You can see that shooting out. All these little wriggly lines, that's all the radar just shooting out and taking that cross section of this storm. So, but like I said, the southwest quadrant is always the area you're looking for severe weather, for a tornado to pop up. Southwest quadrant of a thunderstorm cell. So you always want to look for that. Couple reports. Train spotter reports 1.75 inches of hail, 1 inch hail in those areas, 1.5 inches down St. Lawrence. Alright, so we're going to bring our weather charts back up. Let's see what kind of upper level support we have for this system. Like I said, we had that low pressure system on the surface right over New Mexico. Then we can go up to the upper levels. Let's see what we have at 5,000 feet. All right, we have a pretty strong ridge in the central U.S., so any warm air advection that makes it up to that level is going to be, that ridge is kind of going to stable that out a little bit, and I think that's why we're getting those lower ceilings over. It's all that warm air advection, and the ridging just creates kind of a stable environment while you get low, very low, stable ceilings over the central U.S. So we do have a strong shortwave trough over Colorado, all the way down to Colorado, New Mexico. That's that upper level trough. That's a support for that low pressure system in Colorado. Stacking back to the upper level trough. It's a baroclinic trough. So we do have temperature advection in the upper levels to support that. So that's a pretty significant system right there. Now, for that low pressure system should get kicked off by this major shortwave, that it should kick that system off to the northeast. It will follow the steering pattern. We'll get up to the 700, 500 millibar. We'll see what our steering pattern is, and we should see the direction of that low pressure system. Now, this high pressure system is going to rule, so depending on how fast it moves out of the way, if it's going to block, I mean, it's kind of ridging pretty strong right now, so that's pretty much is blocking all this trough. So that trough just starts to deepen on the west side of that high because it can't move the high out of the way, so it just becomes deeper. And then you got those small high pressure off the west coast. So let's pull up the station plots here. Pretty much moisture all the way through. Actually, we can do one more thing. We can just go ahead and build. We can build a 850 chart with moisture and everything on it. Show us all of our areas of moisture, and then the contours and the isotherms. Here's our major shortwave trough, shortwave ridge over here. And then this map is very disappointing. It's all this black should be green, actually. It should be green all the way through there. This should be all, for some reason the algorithm looks like it reversed on me. So there's no moisture out here. There's significant moisture where the black is, so pretty much imagine this reversed. All the moisture is in the central U.S. Let me get rid of that. Let's go up to the 700. Go ahead and try to run this one. See if we get the same thing on that on the 700. If we do, we'll just continue with the charts up without the moisture. Looks like it. We got moisture to the northeast, moisture to the northwest, nothing in the south. Getting a barotropic. Still baroclinic. We do still got a major shortwave over the Four Corners area, so that's still upper level, pretty significant upper level support for that surface low. Still opposite on the moisture, so we'll just start building the charts from scratch instead of throwing this green up here to distract us where there's no moisture. Now, we know we got all the moisture over Colorado, all over Texas, the central U.S. A little bit, that ridging we had was a little bit as a stretch over Tennessee. We did have that area, little line of precipitation across there too. So we're all the way up to 11,000 feet now. So we're, pulling the moisture up to that level, and we are getting that precipitation over Tennessee from that. So go to the 500. We'll throw the contours. Still got a trough, pretty good trough on the over the Four Corners. Still significant ridging too. So that high pressure, it is supported as well all the way in the upper levels for that ridge. So this low pressure system that's on the surface, it may have a little trouble pushing off. We do have a little bit of baroclinicity there, so we do have a major shortwave over the western U.S. Let's get the station plots on. And still significant moisture, even over the panhandle. We've seen that moisture going all the way up to 40,000 feet. So as far as we go up with these charts, we should see moisture over Texas. Our winds getting up to about 70 knots in the panhandle, about 90 knots over New Mexico, 50 knots to the south central Texas. While we're at the 500, let's go ahead and run a script for the vorticity. That's going to show us our rotation and how significant that low pressure system is for lift. So we do have positive vorticity over the Four Corners, so that is associated with that low. If you look at the vorticity, I'll throw the vorticity lines on here. That way you can see the advection. You look at the winds along these contours, pushing from west to east, and then positive vorticity right ahead of that X, right outside of that troughing area of that positive vorticity. That is where you get the positive vorticity advection. Then you go to negative, and then you go to positive. So the high pressure system, that's downward motion, so that's all negative vorticity, and then you have a little bit of area positive vorticity advection over North Carolina. Small area looks like possibly over Oklahoma, but that's not real significant. I don't see any major advection going on right there. The chart's picking up a little bit, but all your positive vorticity is to the west. Now we can go to the 300. Now we can pull up a chart on the 300. We're just probably going to just see that trough. Let's go ahead and just pull up the jet stream. We can do some color shading with the jet, and that will show us what our steer pattern is also. It looks like we'll throw some streamlines on here. First, we're going to throw the contours on here. 300 millibar. That's 30,000 feet. Still got the troughing, the ridging, troughing. So we're stacked all the way to the 30,000 feet mark. So both these high pressure and that low pressure system do have the upper level support. I'd like to see a jet max. I mean, we're starting to get a little bit of a stronger winds just north of the Four Corners, but sometimes I like to see a jet max pop up right there. That will give that low pressure system some major support and then just suck the mass right out of it, creating a pretty deep low, and then pushing off and seeing where that thing goes, how well it develops. I mean, right now it is a pretty significant system with this upper level trough. You see the isotherms are getting more parallel to the contour, so it's getting more barotropic, and just that's just an indication of a little bit. You know, we got the strong trough, but we don't have the advection all the way up at 30,000 feet, so you don't have a lot of temperature advection. I mean, there is a little bit of weak temperature advection stacked back over Nevada and California. So, I mean, I'm not saying this is a weak low. It's a pretty significant system with upper level support, but the low pressure system was mainly on the surface, and then we went troughing all the way up into the upper level. So the low pressure system has support, but it's not a well developed low pressure system. If it was really developed, you'd start seeing these contours closing off and giving you a low pressure system that is actually vertically, or is actually stacked back a few degrees each level to give you the stack support with closed low pressure systems, and that is a real significant low that can cause some major problems. But this is, like I said, it's not a weak system by no means, but it's not your well developed low that shoots all the way up into the upper levels as a closed low system. There's some these plots are often the balloons that are let loose. 12Z and 0Z. There are so many weather stations across the United States that let balloons go, and the data comes out, and then that sends it back, and that's how we can create these charts for the upper levels. Just the charts analyze. The computer analyzes the data from those balloons that are sent back. All right, so things to look for on the jet stream. I mean, your overall steering pattern. We can throw some streamlines on here. This will show you your flow. We pretty much kind of know what the flow is here. So you see the troughing, the ridging, the troughing. That is your upper level flow. So any pressure system that's steered by this is going to pretty much follow these streamlines. Now, the other thing to look for is like a jet max. If you got, like, this jet max is in the base of this trough, so as it moves into the base of that trough, that's pretty much causing that major shortwave to deepen and maintain its strength. Once that jet max starts moving out, then that troughing will start to fill and to start to level out. So we got a jet max over here moving out of this ridge. So what we could expect is the high pressure system to start to weaken as this jet max moves out, and then that would weaken that ridge and then deepen this trough. If the winds start picking up a little bit more than that, I'd like to see little bit more of a jet max moving into a trough to deepen this trough off the east coast. So, and then that would weaken that ridge. But so it's just another tool to use to kind of get an idea of what the systems, what's happening with those systems. Is that ridge building? Is it weakening? That's just another tool you can pull out to say for a quick look. And it's not always correct, but it's just one other indicator to look for. So we could go up to 250. Let's just go on up to 200. Pull the winds at that level. Now we just have winds all over the place. So still got that troughing, bridging. We have our support. Maybe picking up a little bit of maybe the subtropical jet way up in the upper levels. We'll start seeing more of the subtropical jet as we approach summer. Start seeing these jet maxes over the Atlantic, over Mexico. And we still got some pretty significant, A little bit of troughing there. I mean, it is leveling out a little bit. That ridge ain't even leveling out at, all the way up at 200 millibars is approximately about 40,000 feet. So, but we got moisture over Louisiana, a little bit over Mexico. Um, we did see moisture on the radar all the way up to about 40,000 feet, but this didn't pick it up. We're probably just it's got to see a what's a dew point depression is a 10, so we're probably a little bit above that. Drop down a little bit, you probably start seeing that moisture. So we're pushing almost 40,000 feet, but the 40,000 feet we've seen that blue, so that could be just radar picking up some just some clutter or something too, just something out there, just making a kind of running the algorithms, been just kind of extrapolating some data. All right, so I guess we can pull up some models. I haven't set up the screen for the models yet. Maybe I'll leave the radar up for you for a second, and let me go pull up some models real quick. All right, here we go. So, tropical tidbit showing the low pressure system over the panhandle of Texas. Looks like it's showing some weak moisture to the south, most of the convection to the north, and it's a little backwards of what time we got here. 0Z, it's about 7 o'clock. So, these models are not initializing very well as far as that severe weather. Let's go see what we got. Now it's pushing off the convection, mainly over Oklahoma, and then just kind of pushes a little bit further north for the convection side of it. The snow's there. We got the snow over Colorado. Low pressure system. See, it just kind of did a big old loop right there, kind of waiting for that ridge to weaken so it can just move out of the way. Now, as we move on into Monday, it looks like that ridge moves out and allows the low pressure system to move north. So, creating some wraparound, pretty strong wraparound moisture. Wyoming getting some upslope flow there with the moisture and getting up into the freezing levels and getting some snowfall there. South Dakota, all the way into Iowa, southern Minnesota, Wisconsin, mixture. Pretty much the rain through St. Louis area, all through Missouri, the convection, moving to on the southern part of Missouri, and then the snowfall up into Wisconsin, and then the frontal passes coming into the Ohio Valley. So looks like it's getting pretty weak though. Looks like a mixture into the Appalachians, and then snow over the Great Lakes region. So that pressure system pushing off, and then now we're getting the high pressure system. See how that as that pushed south. Now we're getting the southerly flow with the onshore flow again, and now we have another low pressure system over Oklahoma. Probably look for some more pretty good weather along that system too. These models, like I said, they weren't initializing well with this system, so the next system that develops, they're probably not doing very good either. So, but all this warm, moist air being pushed off the Gulf, you got all the moisture you need to create that line right all along through there of convection can happen at any time. So, not sure where I hit a home button or something. So, go back. All right, so there's our line. Convection pops up over Tennessee, Kentucky. That low pressure system moves out of Colorado. Starts pushing to the northeast. Still some snow for Iowa. And some thunderstorms in northern Illinois. Then we got some pretty good convection over the mountain range. Over northern Georgia, South Carolina. Then that low pressure system pushing off and high pressure building in. And this is 18Z. That's 1 o'clock on next Saturday. March 20th. And then it should be clearing out pretty good there with that high pressure system. So looks like another front stretching down from the north, going through the central U.S. But other than that, that's pretty much it for this video. I'm going to leave that here, and if you like the video, give me a thumbs up. If you don't, give me a thumbs down, and I'll see you on the other side. Thanks for watching.